Well, first I would like to thank Jamal for organizing that. It's always good to have opportunities to share what we like, and in this case, I like to share a little bit my experience on applying machine learning to geosciences. I made it as fairly informal, so if you have any question you want to discuss a specific slide, a specific point, don't hesitate. It's not formal at all, and yeah, they want me to be louder, so I'll try to be louder. Okay, all right. So yeah, the aim of the presentation, as I was saying, it's an introduction to machine learning. It's not to teach you how to do machine learning. Unfortunately, it takes more than 1 hour and a half for that. It's just to address how it is applied, give the background, a little bit about the basics of machine learning, and then showing you examples, case studies of how it can be applied, and give you ideas about how it can help you solve your problems, and give you the will or the desire to learn by yourself how to do machine learning and data science in general to help you in your everyday life. First, a little bit of corporate, of course. I'm from SRK Consulting, which is a consulting company. It's international. Basically, it's a technical consulting practice that's all over the world. We have offices everywhere. I learned a few days ago that we had an office in Kazakhstan. And we do from exploration to mine closure. Here in Toronto, we have mining engineers, people doing resource estimations, and we have a structural geology team, which I'm part of. So that's me. I'm a consultant in structural geology. So basically, I'm more a field geologist. I like to go in the field and play with rocks. But especially if they are very metamorphosed, very deformed. But I also apply machine learning and data science in general to solve problems. And I like to promote the use of these tools because I think they are not known enough. Their potential is not known enough. But their how do I say the issues using them as well are not known enough. So you might have noticed that I have a slight French accent. So if you don't understand what I say, just ask me and I'll try to repeat with a better English accent. Now that I've presented myself, I'd like to know a little bit about you. First, who is a student here? And who is a professional? And who is working in geology in general? Oh, not everyone. So what else are you studying or working in? Engineering? Okay, and geophysics? Okay, so I think that's pretty much everyone. Okay, so we have a very diverse attendance, but the way I try to do it is to not to go into the details within the mathematics behind that, within the exactly how an algorithm is going to work. It's going to be very practical, giving examples of how it works, what are the products, and if you have more questions, maybe during the presentation or after, we can discuss about that. I'll start with what exactly is machine learning. I think we still hear a lot about it, not only in geosciences, everywhere, and it's mixed with many different words: artificial intelligence, data science, data mining, neurocomputing, and all these things. It's a little bit of everything, and it's something on itself. So I'll try to define exactly what is machine learning before we go a little bit further. So if you look at the definition you would see in a dictionary, machine learning would be an advanced numerical method that allows data-driven predictive modeling. So you ask a computer to make a prediction, and this prediction is based on the analysis of examples. So you give data to a computer, it's going to learn a pattern and make predictions based on this pattern. The term originated in the late 50s with IBM, but at that time the field wasn't much. It was part of artificial intelligence, so the goal to create a thinking computer. Now it's a completely different field, and it flourished in the 90s with the rise of computers that were good enough to apply these algorithms. And deep learning, which is part of machine learning, started to pick up in the early 2010s for the same reasons. Before, we had not the computing power that enabled us to apply these algorithms. But deep learning is there since the 80s. And there's plenty of applications nowadays. Self-driving car, Cortana trying to answer our questions. There's Amazon, which knows better than us what we want to buy. YouTube, which knows better than us what we want to watch. But there is one example which I think is very close to what we do as a geologist. This is so from a more health or medical publications. In many applications, the performance of machine learning-based automatic detection and diagnosis systems has shown to be comparable to that of a well-trained and experienced radiologist. And I think you can replace the word radiologist with geologist, meaning that for some tasks, an algorithm can do as good as us. But still, we have radiologists, right? When you go to the hospital, it's not an algorithm telling you if you have a broken rib or whatever. Because the algorithm is making a prediction, but you still need an expert to take this prediction and to make an interpretation based on that and to make a decision based on that. You won't leave the algorithm make the decision for you. And now the question is, how does a computer learn? How do these algorithms learn? I like this simple example of if you have an equation. So here, y is equal of f of x's, x's being different input variables you give to your algorithm. You know that y, what you want to predict, has a relationship with your input variable, your x's. And so there's a function that can transform these x's into a y. What machine learning does is you give example of your x's, of your y's, and the algorithm is going to try to find an estimation of this function. It's going to try to approximate the way to transform these x's into y's. And once you have this approximation, you can apply it on new x's. So there is this example. We have red dots, blue dots. This is our y, either red or blue. And our x's are the x and y axis of this diagram. And we have example of different algorithms trying to find the best approximation to the function that transforms these x's into a y. And you can see that different algorithms perform differently with more or less success. So the idea behind that is once you have, so for this example, you have a geological map, you have all the geological information, which is your x's, and your y is there a deposit or not? So you give examples of existing deposits with the related geological environment. You have your algorithm learn the relationship between geology, geophysics, geochemistry, and the presence or absence of a deposit. And once you have trained your algorithm, you can ask, okay, now that I'm giving you back this area, this geological map, where am I the most likely to find a deposit? It's going to make a prediction. The thing is here that we just give the data to the algorithm. We don't say faults are the more important. Geochemistry is the most important. You have to weight it this way or this way. The algorithm will do that itself using the examples we have provided. But so that's why we say it's a data-driven process. But in the reality, we are the ones choosing what data to give, in what format to give it. So it's not entirely unbiased, and there's a strong influence on the user when you look at the end product. There's different types of machine learning algorithms. So I'll go in general through the different categories you can have. The first grouping you can have is between supervised and unsupervised learning. Unsupervised, just you pitch the data to an algorithm and you ask, well, what can you find within the data? So for example, here, there's obviously two groups, so you would expect an algorithm to outline this as group 1 and group 2. Supervised is you know what you want to predict, and you have examples of what you want to predict. Here are orange dots, blue dots, try to find the best algorithm, the best function to divide these two groups. Now, a specific task is classification, when what you want to predict is categorical. It's either basalt or rhyolite. It's either mineralized or not. Then you have the regression. What you want to predict is a number. it's I don't know, for example, alteration intensity, probability of having a deposit. And in this case, the data is continuous, it's not a category anymore, and it will be called a regression. Then there is reinforcement learning. I haven't found any application of that in geoscience, but I think it's a pretty cool example. So this is basically you provide an algorithm with just, so the algorithm tries things and you say it's good, it's not good, it's good, it's not good. And it tries to improve every time and every time to get higher scores. It's called reinforcement learning, and that's, for example, what Google has used to beat Go players a few years ago, or chess players. So it's very nice to have a computer learn, but at the end of the day, what we want to do is to predict. So as I was saying, what the algorithm does is not finding the exact function that transforms your X's input into a Y. It's finding an approximation to the best of its capabilities. So you have to always know that what you're playing with is an approximation of this prediction with some uncertainty. Here, for example, we have this limit is here. It's a straight line, but maybe in reality it's not a straight line, but we don't have enough training point to define an exact, more precise boundary. So we always have to have that in mind. And that makes us come to the difference between underfitting and overfitting a model. Because if you have a series of values you want to predict, so we have this example of a lot of black dots. An algorithm can come with many, many different answers to this problem. But we want one that's going to work on new data. So for example, here, you have a straight line. Oh, maybe it's an interesting way to predict this data, but it's not precise enough for us to use. At the other end of the spectrum, we have this very intricate curve that's fitting all the points. So it's the best algorithm ever. It's 100% accuracy. But I wouldn't use that to make prediction in real life. You want an algorithm that's good at generalizing, which means it has learned on training data, but it's able to make good prediction on new hidden data. And that's where it comes. You have to understand a little bit what's behind the hood. Unfortunately, a lot of the machine learning algorithms are not easy to understand. Some of them are really, really simple. You can just read the answer. If rock is gray, it's a rhyolite. If rock is dark gray, it's a basalt. That's an easy one. But if you want to make complex prediction, you'll need a more complex algorithm. And then it's going to be a black box, which means it's not possible or not very easy to actually understand how the algorithm is making a decision. You give it a picture of a rock, it's going to say you, well, this is a granodiorite, but you don't know why it's saying it's a granodiorite. And because there's a lot of algorithm, there's a lot of different ranges of explainability, which means the algorithm giving you the recipe it uses. And the issue is that usually the best the algorithm is, the better it is at making complex prediction, well, the less explainability there is. I'll give a simple an example here, decision tree. So that's what I was saying. Depending on the color, whether it's gray, dark gray, it's going to be a basalt rhyolite. You can just read it, it's easy. Deep neural networks, at the other end of the spectrum, they can do amazing things, but you just can't understand what's going on. It's millions of neurons connected to each other, so it's just impossible. And there's plenty of these algorithms, and some of you probably have done machine learning in the past without knowing it. Just simply doing a linear regression, by definition, this is machine learning. You're learning from data, and you can make predictions. For example, kriging, by definition, this is machine learning. There is instance-based algorithm. This one is really simple. If you have a black dot, and you want to predict whether it's within the red or the green group, well, you just look at the closest samples. If they are green, well, you're likely to be within the green group. They're more complex. Well, not complex, but they're decision trees, which are very easy to understand, but it's hard for them to make complex prediction. There's Bayesian probability, which is basically statistical machine learning. You have deep neural networks, which are kind of the buzzword with all these self-driving cars and things like that. and ensemble methods, which is basically take a lot of different algorithms, average all of the results, and get a better prediction. I'll go through a few of these algorithms. It's just to give you an idea of what they are exactly, how they work, but it's not meant to be giving you the key to the best algorithms ever. It's just to give you an idea of what they are. One of the simplest algorithms is the k-nearest neighbor. So basically, it's mainly for supervised classification. You can also do regression with it. And so that's the example I was talking about earlier. If you have a sample you want to classify, just looking at the k is equal to 1 at the one nearest sample. If it's a red square, it's likely the sample you want to predict will be a blue square. It's likely the sample will be a blue square. But maybe you want to look at the broader population, so you'll look at the 3 nearest neighbor, and maybe you'll have a better, more accurate prediction. So that's as simple as that. So the parameters you can tune is either the number of neighbors. You want to look at 2 samples. You want to look at 25, 100 samples around the point you want to predict. And you want to weight each sample based on the distance to the sample you want to predict or not. That's the only parameters you can play with. That's an example of what you can do with k-nearest neighbor. So very simple one. You have silica, magnesium, and I did put some example of basalts and andesites, and ask the algorithm to produce a function that separates basalts from andesites, and that's the type of results you would have, which is fairly precise, close to the where there is a lot of points, and start to be not broad and rough outside of the where the data is. So we've seen supervised classification. Now, unsupervised classification, one of the simplest algorithms out there, is k-mean clustering. The way it works is very simple. It's basically, you say at the beginning, I think I have 3 classes, 3 groups, and it's going to produce 3 random points. Then it's going to look at it's going to attribute to one of these points all the samples that are the closest to it. So here, all the samples that are closest to the red cross are attributed to the red cross, etc., etc. And once you have done that, using all of these samples, you recalculate the average value of all these samples, and you move your red cross, for example, to this new average. So it will have moved, all of the 3 groups will have moved, and you can now recalculate again the average of all of these samples. And little by little, the groups are supposed to center on each actual cluster in the data. And here's an example of k-mean clustering on the same data set. Here this time I did put basalt, andesite, and dacite. And you can see, okay, so first there's the data on the left. In the center, I asked, okay, give me 2 clusters. So that's the result. And then after, give me 3 clusters. That's the result. And then you would have basalt and andesite and then dacite. So I've shown you the most simple algorithms out there. I'll directly jump to what I think are the most complex ones, but that's because there will be examples with them, and I want you to understand why they are performing differently from the other algorithm types. So you can use neural networks and deep learning for pretty much everything, even more tasks than normal or shallow machine learning algorithms. And basically, neural networks are based on neurons. They are just networks of neurons which are just values. So basically, we have this example of input data. So is the rock green? 1 is yes, 0 is no. Is the rock coarse grain? 1 is yes, 0 is no. And then you connect these initial neurons to the next layer of neurons with a multiplier. So for example, here you multiply 1 by 0.8, and then you add plus 0.73. So it's just linear combination. And this neuron is fed by the first 2, this one same thing, but every time with a different linear combination. And then Next layer, which is here the output layer, will just again combine the results. So again, same thing, linear combinations, and you'll get an output. Here in this case, it's a 0, so it's a gabber. It looks very simple, but in reality, it's because you have just a few neurons. But when you get architecture with millions of these neurons, you can start to make very, very complex prediction in very complex systems. So how do we give weights to these neurons? How do we multiply one neuron to form another one? It's using what is called the gradient descent. So basically, you're giving your training data to the neural network. Initially, all the neurons are random numbers. You give the data, and then the algorithm looks, oh, okay, I did well on this neuron, I didn't do well on this neuron, etc. What can I do to improve? Not to be perfect, just to improve a little bit. And it's going to say, okay, I have to change this neuron to work, like I have to increase this neuron, decrease this one, increase this one, decrease this one. And this is what is shown here. Imagine this is the weight of a neuron, and you have the target, so the optimal value of your neuron. And you start here, and you say, okay, I have to go to increase the weight of my neuron, and I'm going to improve. Increase again, oh, still improving, increasing. When you arrive here, oh, I'm increasing, it's not good, so I have to stay down, and then you have optimized your problem. That's the type of results you would get using a simple neural network. So same example with the basalt andesite. You have the example of the nearest neighbors, and then you have what you would obtain with a simple neural network here. So what looks like a more smooth prediction here. If you had more neurons, more hidden layers, you will have a more complex prediction. Now, what we have seen is shallow neural networks. What is deep learning? It's just basically add layers of neurons. The more complex the problem, the more layer of neurons you add. That's just basically what it is. I think some of the Google algorithms are tens, if not hundreds of hidden layers. But personally, I don't think I've been over like 6, 7, and it's already very, very complex. As many as you want. So yeah, that's the issue with deep learning, is that there are so many parameters you can tune. You can tune the number of layers, so you have to decide how many layers. But for each layer, you have to decide how many neurons. And usually you want to have, for example, more neurons in the first layers, and then little by little, it's learning the more complex patterns, and it doesn't need as many neurons. And you reduce the number of neurons until you arrive at your outputs. And the neurons within a layer, they don't correspond to each other. No, exactly. No, they don't communicate with each other, but each neuron communicates with all the neurons to the next, to the previous layer. Yeah, in theory, in practice not, but in theory that's how it works. Sorry, can you just repeat that? Oh yeah. So I was saying you can add as many layers as you want, and you tend to add more neurons to the first layers, and then reduce the number of neurons toward the end of your network, because the first layers will be used to learn the small patterns within the data, the small relationship between 2, 3 variables, and as you go into your model, it's going to start to learn more complex patterns, and because there are not as many, you don't need as many neurons. But in general, this is not a real science here. This is more craft work, I would say, in the term that there is no rule on how many layers you need to do. It's just trial and errors. Can you say the limiting factor is your processing problem? Yes and no. The issue is that if you have an algorithm that's too complex for the data you have, it's going to do overfitting. So instead of learning the pattern within the data, it's just going to learn the data. And it's going to be able to predict perfectly your training data set, and it's going to be rubbish on new data. So you want to have an algorithm that's okay, deep enough to learn the complexity of the model, but not too deep. So there's a precise point where you want to be.
Do you cross validate to determine how many layers you want?
Yeah, that's, well, we're gonna come to that later, but that's what you have to do all the time in machine learning is to have training data and testing data, and you don't want your testing data to basically be involved into constructing the model, so that the model is not influenced by this data, and that it's surely hidden data on which to test the model. And deep neural networks can be used for so many things. As I was saying, you can tune them with different the number of neurons, number of layers, and there's many different architecture to do many different things. To beat a player at a video game, to drive a car, to predict rock names using photos. There's many different applications, and for each application there's a different architecture. But there's one architecture specifically I want to address, because that's one that's used a lot in geosciences, which are convolutional neural networks. That's basically what is used to recognize images. When you see that Google can, or anyone can make the difference between a cat and a dog using a machine learning algorithm, that's using convolutional neural networks. So the way this works is, instead of having each of your neurons connected to the next layer, it's looking at patterns within the data. So you're providing, instead of providing a line of neurons, so your data as a line or a line within your spreadsheet, you actually provide an image, a grid, or a 2D, 3D, 4D grid. And instead of having linear relationship between neurons, it's going to apply a filter, a convolution for the one doing geophysics. So basically, this filter will be, in this example, this filter has only zeros. Here it's a 4, here it's a -4. And you're going to apply, so for example, if you want to apply this filter to this pixel, basically you're going to multiply 4 by 0, -4 by 2, etc., etc. You're going to multiply all of the values here. And the cool thing about that is that you're going to be able to extract a pattern. So for example, here, if I have high values here and here, is going to create the output will be pixels with high values here, and you don't care about the values of the pixels here. So it's extracting a shape. If you had high values in your filter doing kind of a corner, it's going to extract corner shapes. And at the end, there's going to be a value that's going to be imputed, so multiplying all of these pixel values from the filter to one single pixel is going to extract this pattern, and you're going to have a high value if you have a corner, and a very low value if you don't have anything looking like a corner. And then same thing as any other deep learning algorithm, you can stack this. So you'll start with a raw image, and then you'll first layer of filters of convolution. So you'll have, which will be all your the equivalent of your neurons, each convolution being a different neuron. You'll add all of these, and then you'll have a new layer of convolutions again and again, and at the end you'll connect all of these to a standard layer of neurons before your output. And the way it works is that first you'll apply simple filters that will extract, for example, a corner, a line, things like that, and at the next layer is going to be a pattern a bit more complex. A circle, a square, a triangle, and little by little you'll be able to extract fairly complex patterns like the window of a car, a wheel, the face of a dog, things like that. So the idea is to start simple and to learn little by little more complex things. The thing is that they are extremely powerful, but they need a lot of training data. So you can just, with one picture of a dog, one picture of a cat, train an algorithm. It's thousands of images to be able to have something that works properly and generalize as well. And as I was saying, these are just examples of algorithms. There's plenty out there. Naive bias, random forest, or other ensemble methods are really powerful. Supervector machine is extremely good as well. For clustering, there are more complex, more powerful algorithms like self-organizing Gaussian mixtures. I could go on and on and on. For each problem, there is an algorithm. And I would say, if you're a practitioner, don't stick to a specific algorithm. When you have a new problem, try everything, or at least what you think could work, and then come up with what you think is the best algorithm. So how do you apply in real life these algorithms? Actually, the process of training an algorithm is maybe 5 or 10% of the actual work. First, you have to articulate the problem, know what you want to do. As you want to predict something, do you want to understand something, what exactly? Then you have to collect data. Collecting data doesn't necessarily mean to go in the field. It means to, okay, to look at what's the historical data, what's the public data, what do I have, what's the state of that, can I use it, is it digitized, is it just hand-drawn maps? Then you have to do formatting of the data. That's maybe what takes the most time, meaning having clean data. In all the exercises we have in our life of geoscientists, we have to clean data. For example, resource estimations, targeting. But when it comes to machine learning, these algorithms don't take anything not correct as an input. You have to have everything perfectly clean. And so that obliges you to have a really good quality process. Once you have formatted your data, you have to do exploration analysis. It's not good to just give the data to an algorithm and take the prediction as an output and be happy. Yeah, it's okay. It's telling me it's working like that, so I'll take it as a success. It's always important to understand your data, how it works, what is the relationship between all of your variables, what are the possible issues with data distribution, collection, etc., so that you are making an informed decision when taking the output of the algorithm. Then you have to clean your data again to give it as an input to your algorithm. You have to balance to scale your data because if one variable is varying from 0 to 1000, one other from -1 to 1, they're not at the same scale, and the algorithm will think the one from 0 to 1000 is more important to the one from -1 to 1. So you want all of your data to look alike, and there are plenty of ways to do that. Then comes the actual training, which is giving example to an algorithm for it to learn. Once you have done training, very importantly, you have kept aside a little bit of data to test the algorithm to see how well it performs, to have an idea of how good the prediction you're going to use are. And once all of that is done, well, you're good to go. You can do prediction on your data. So I won't go into too much detail into that because it would take one entire day. But I'll just go a little bit over the training part because I think this is something very important and this is something that's not always done properly. So once you have a clean data set, you have done all of this 90% of the work, which is preparing, cleaning, formatting the data. The next step is to train your algorithm. So you'll divide your data. First, there's your training data and the data you want to predict. If you want to do prediction, well, it means you don't know the output, so you can't even feed it to your machine learning algorithm. The training data, then you'll divide it into two. You'll take the training set to actually train your algorithm, and the testing set, which should be kept hidden until the end. Once you have your algorithm, you want to test its performance. And again, once you have a training set, you want to test a lot of different algorithms. You want to test different parameters within your algorithms. Do I need the 3, 5, 10 hidden layers? That you do, and so you want to know how well all of these possibilities perform. But you don't want to test these possibilities on testing data, because if you do, you have influenced your trained model with your testing data. Your training model will be optimized for your testing data. You don't want to do that. You want to keep it hidden until the end. So what you're going to do is to divide again your training set into a training and a validating set. And you're going to use this validating set to choose which model works the best. Once you have done that, so which is training a model, you'll choose the best tuned algorithm. You'll retrain it on all your training and validating set to get your final model. And once you have done that, you can test the performance of this model on the testing data. So the model has seen the testing data only once, right at the end. So you can be sure that the prediction will give you a good idea of the generalization of how well your model will perform on new data. And once you're happy with your model, you think you can use it for real life prediction. Well, now you can take your the data you want to predict and make new prediction. So yeah, that's it in terms of the uh, basic background on machine learning. So before immediately jumping to examples, do you have any questions?
Divide and say that, divide 50/50.
There's no rule for that. It's an equilibrium between you want to have enough data to train a good model, because if you don't have enough data, the model will be crap. But you want your testing set to be representative of the entire population you will want to do predictions on. So sometimes it's 70-30%, for example. Sometimes you have a lot of data, so you take 95% for the model, 5% for testing, and you can even do cross validation as well. Yeah, exactly. But that's for. Oh yeah, sorry. So the question is, how do you divide the training and the validating, or the training and the testing sets? And the answer is there is no rule. So it's a bit by experience and how well you understand the data, because you have done your exploratory analysis before.
One, yeah, yeah. One last question. You didn't talk about dimensionality or that. Are you going to talk about that?
No, I'm not gonna talk about that. That's in the pre-processing. So the question was, I didn't talk about dimensionality reduction. So, for example, removing redundant variable, or doing principal component analysis, these kind of things, or just taking the 10 best variables. This is something you usually do. This is part of the process, but I won't go into too much detail, because that's another 1 hour in itself.
I'll start like nothing about dimensional reduction. Normally in geology, you don't have that much data. And if you do geoscience, let's say they want to do sentiment analysis, they have so many parameters, thresholds, so they have millions of records and millions and let's say hundreds of even thresholds. What they do is PCA to reduce that and solve the problem while conserving the variability of the data.
Yeah.
And I think in geology it's different. You are limited to the data and you don't want to miss anything. You want to include everything. That's one thing. Another question that I'm going to ask is, do you have goals in applying clustering into spatial context where you do spatial clustering?
Yeah. So I've done a little bit of spatial contouring. So the question is, have I tried to use clustering in spatial context? I've done a little bit, and I've read a few publications about that as well. It's a complex problem, because the issue with that is that, for example, if you have a rhyolite, and there's a lot of rhyolite up there, and a lot of rhyolite to the north, or a lot of rhyolite to the south, it's going to end up as two clusters, because because the geoference is an input variable. So sometimes it's a good thing, sometimes it's not a good thing. And in some applications, you want to put the coordinates, the x, y, z coordinates of each data point you have, and sometimes it's not a good idea, because it's going to be biasing your data.
I agree with you, because we did a research when I was studying at CCP, and we didn't include the XYZ as coordinates into the cluster. We did some multivariate spatial clusters. So we ended up with clusters that is stationary, so that we did estimation and simulation within those. They might not have some geological meaning for someone, but they are good in terms of stationarity.
Yeah. So it's again, it comes to the exploration analysis you have done, how well you understand your data, and you'll come up with, okay, maybe it's good to include XYZ coordinates for what I want to predict. Maybe it's not a good idea. And sometimes I'm not sure, so I'm trying both. And just to have an idea. So yeah, and there is so it's something I'm less familiar with, but people use also distance matrices to as input variable instead of XYZ coordinates. But I'm not just a statistician, so I won't comment too much on that.
But
Yeah. Yes. So the question is, when do you know that you have overfitted? Whether it's testing or validating, if you have done your validation process well, you'll immediately know because the validation data has not been given to the algorithm when it was learning. It's just for testing different parameters. So you'll know. One thing you have to be careful with is with georeference data. So that's what we're using in geoscience. Here's a bit tricky. So for example, if you have a data in boreholes, you can either split your validation data randomly, like 50%, 50%. The problem is you'll have points that are very close to each other in space, which are in the training and the validating set. So the model will be optimized for your training set, but your validating set is nearly identical because all of these points are close to each other. So for example, when I'm playing with boreholes, what I'll tend to do is I take, for example, 10 boreholes for training, 2 for validating. If I'm playing with a map, I'll cut the map in like 5 or 3, and I'll take 1 part for training, 1 part for validating. So you have to be very, very careful that if you do this training validating part properly, you will see that one model that performs very well on training data will be rubbish on your validating data, and then you know, okay, this is overfitting. If your model is bad on both, this is underfitting, and if the model is good on both, this is good fitting. Okay, good. So now, oh yeah, go ahead. The question is what are the practical applications? And that's very good because that's the next part of the presentation, which is I'm going to give examples of applications. So it's not showing everything that can be done. It's just giving you examples of what is the potential, and but also, what is the potential, what you have to be careful about, what kind of data you can use, what kind of data you should not use. The first example, this is training an algorithm to recognize lithologies based on core photos, and from that to generate pseudologs. So I like this picture here. So basically, as a geologist, what we do is just human learning, I would say, is we look at rocks. From there, we say, okay, based on these characteristics, the rock is a basalt, it's altered, it's mineralized, etc. So it's just applying the same thing to a machine learning algorithm. Image, rock name is a function of the rock image. So in this example, what we have done, so that's prior my time with SRK, we have taken high definition images along a jury core, and we have trained an algorithm using a description from who we thought was an expert. So that's the problem when you look at geology. You give the same core to 2 geologists, you come up with 2 different logs. So we had to make a choice and choose one of the logs. And basically, we sliced the entire borehole into 10 centimeter long images. And if you zoom in on an image, it's just basically pixels. And this pixel, in each pixel, you have red, green, blue value. So it's just numbers, basically. So once you extract these numbers, you can apply what we've seen before, which is a convolutional neural network. So I won't go into too much detail because you've seen that before, but basically you give the rock, first layer will extract simple patterns, and little by little, layer by layer, you start to extract more complex patterns until you have a flat layer at the end, which takes all of the information from all of your different convolutions to give you an output, which is the rock name. That's the type of result you would get. So in this example, we had 90% accuracy relative to what the geologist logged. So it's not 90% accuracy relative to the reality. We don't know the reality. It's just 90% relative to what the geologist logged. That's what the prediction looks like. You can see that it's very noisy at the beginning. The reason why is because you provide the algorithm with just a 10 centimeter long picture. You don't give it context. So once you give it a little bit of context and you smooth the prediction, that's the type of log you get. And you can compare it to what the geologist has. And it's very similar, but there are differences. So for example, here, the algorithm said there is a diorite dike. Here, the geologist said there is a gabbro. This, I think it was actually a gabbro. I'm not sure. Here, the algorithm has seen a gabbro dike within the diorite that the geologist didn't see. And this one here, the yellow, so the rhyolite interval within the diorite, I think it's very interesting. So I went to see the core pictures, and actually this is a silicified interval within the diorite. So the algorithm has learned with examples, and it has seen that this rhyolite has a light color, and it's given a light color of rock. It doesn't know what silicification is. It's just been told these four groups. So, okay, this looks like a rhyolite. I'm going to predict it like a rhyolite. And that's the reason why you need a geologist at the end to have a critical interpretation of the results. The neat thing about that is that it took less than 10 minutes to build this 800-meter long log. And what takes more time is for the computer to open and close pictures. The prediction itself, it's just merely seconds. Another example, how to train an algorithm to recognize what's called invisible gold mineralization. So in this example, we took rock physical properties. So we don't use that much in the mineral industry, but that's a standard in oil and gas. It's just resistivity, conductivity along hole, gamma rays, neutrons to get the density, and seismic properties, etc. It's measured along the core at a very small intervals, so it's very continuous data. In this case, it was in a deposit where gold, it's a massive sulfide deposit, but gold is not always within the massive sulfides. It's sometimes disseminated within the rock, not associated with sulfides. And the problem is because it's a mine that's mined by mainly by people who were used to base metals. If there's not much sulfide, I'm not sampling it. It's not worth it. So not like some intervals of gold were missed. So the idea was just to look how is it possible to help a geologist with selecting which intervals to assay. Not to say there's that much gold in a rock, just to say is there gold or not. So in this case, so this example, it was just predicting whether there is more or less than 1 gram per ton gold in a rock. The input were all of these rock physical properties. And that's a good example of training here. So we did training using cross-validation. So we took the data set, and then we divided it into 11 holes for the testing, 11 holes for training, 3 holes for testing. But 11 holes is not that much for training, so you don't want to divide that in 2 and doing training and validating. So what we did is what is called cross-validation. So every time we wanted to test an algorithm with a different set of parameters, first, you do a first test by taking just a little part of the data as validating. You train on the remaining data. You test on the validating data. And then you do it again, same algorithm, same parameter, but with a different validating set. And you do it over and over again until you have validating against all of the training data. And once you have done that, you average all of the scores, so how well the algorithm has performed, and you know which algorithm is better than which other. Still having the validating data hidden from the training data. Once you have selected the best, what you think is the best algorithm with the best parameters, you retrain the entire thing with the entire training data, and you can do a test here. The type of results you would get, that's the type of results. So you have on the left the actual gold rate. You can see it's not continuous because geologists don't sample the entire borehole. You have the probability of gold being higher than 1 gram per ton, and this is continuous because rock physical properties have been collected on the entire borehole. It's just that here you don't see anything because the probability is 0. And we can see that every time you had a little bit of gold, the algorithm was able, or nearly every time, was able to predict that there is gold. So it was more of a thought project, because in reality the problem is that by the time you have collected rock physical properties, the geologist will have logged the core and will have taken all of the samples. But it was a good example to see the potential use of such type of data sets. Here what we see is that, okay, maybe the algorithm is able, using rock physical properties, to predict the presence of gold, but it's not because these rock physical properties measure gold in a rock. It's because gold is associated either with alteration, with a specific rock type, with things like that, and the algorithm is able to make the link between rock physical properties that change along the hole and the presence and absence of gold. And the same thing as in the previous examples, the final decision should always be done by a geologist. If the algorithm says there is no gold and you see a visible gold, well, maybe, just maybe, you should sample. Another example, so this one is not mine, but I think it's very neat. It's automatic fracture detection. What is fracture detection? This is something that we do it a little bit in the mining industry for geotechnical purposes. But they do it a lot in the oil and gas industry because fracture means separation of fluids, so that's really important for them. It's basically mapping the fractures along the drill core within the hole in this case. So not on the drill core, but within the boreholes. Using downhole imagery, so it can be photos or it can be sonic images. That's an example, so acoustic images. Here is an example of fractures within an acoustic image. So you can see these slightly light color bands. These are fractures. So you have someone in front of a screen mapping separately each single fracture for days and days and days. It's not a very nice job. It's a long and tedious process. So the idea is to automatize that because it doesn't require huge expertise. It's just repeating the same thing again and again and again. They have been trying to do that in the oil and gas industry for a long time, long before using machine learning. The issue is that the algorithms that are able to automatically map these fractures, they have way too many false positives. So one of them is called the Hof. Oh, I'm not pronouncing that right. I'm not even gonna try. The Hof transform. And you have an example here of what the output is. And everything you see, so the green lines, the red lines, according to the Hof transform algorithm, this is a fracture. But you can see that there's too many of them and they're not realistic. So in this example, what they did is instead of just taking the picture and trying to predict the fractures, is they took the result of the Hof transform and just asked the algorithm, is this a real or false fracture? And basically the idea was to use deep learning to remove these false positives. So that's an example of training a deep learning algorithm. So if you remember what I was saying at the beginning, you don't provide all of the data at once. You give the data the first time, or maybe just part of the data. The algorithm, the deep learning algorithm, we use gradient descent to improve a little bit, and then you give the data again, it's going to improve again and again and again. And that's that's a neat way to show that. So you have the number of epochs, which is how many times you have provided all of the data to the algorithm. And for each epoch, it's computing the accuracy of the model. And you see at the beginning, the model is random, it's performing very poorly. It improves until it reaches a plateau. And in this case, what they use for training data, it's basically someone had to manually say it's a false positive, it's a false positive, it's a true positive, false positive, true positive, and provided this information to the algorithm. And here are a few photos, like images to show the results. You have manual marks, so what a human being would do. You have the results of automatic classification of the marks by a geologist, by a deep learning algorithm. You have in green what the algorithm has predicted as true positives, and in red as false positives. So it's performing fairly well. Another example, this one is geochemical. If I'm going too quickly over the examples, if you have any questions, don't hesitate to interrupt me. I think I've put way too many examples, so I want to show you everything. So I'm going a bit fast. Yeah, am I doing good in time?
Yeah, the piece is here.
Okay, all right.
Your top is one way.
So yeah, geochemical mapping. So in this example, so we are in south of England, and this is metasedimentary province intruded by granite plutons, and they had soil samples, and they just wanted to do interpolation of these soil samples. So what you would usually do is screening, just taking all of these samples, doing a geostatistical analysis, and end up with a grid showing you the values of, for example, lanthanum or aluminium over all of these soils, or what is predicted using kriging. But here, what they tried to do, or what they did, is instead of doing kriging, is they just train the algorithm with existing samples together with, as input data, satellite maps, terrain topography, geophysical maps, so data that is continuous over all of the area of interest, together with the existing value for soil samples, with all of the geochemical elements you can think about. So basically, the input data, as I was saying, elevation, terrain parameters. So from the elevation, you can extract the slope, the curvature, the wetness index. I think it's calculated from satellite data. I'm not too sure. Raw Landsat data. So it's 10 input variables. And then some geophysics, so gravity, magnetic, radiometrics. And in this case, for example, they didn't use coordinates. So if you're doing kriging, the only input you have is coordinates, basically. Coordinates and the value of what you want to predict. Here, in this case, they don't give x, y coordinates of the sample. The algorithm is not given this information. And what they wanted to predict are these 48 elements. So what do you think in this case this exercise is? Is it a regression or classification? Yeah, exactly. So compared to what we've done before here, this exercise is a regression, trying to.
So compared to the kriging, are you higher
we can see that the variability, that's a good question. There is maybe a higher. I don't remember if they addressed that in their paper. Actually. Yeah.
You compare kriging results and organic kriging results.
Yeah. Yeah.
That's secondary.
No. The only input variables for each prediction are these.
Yeah. So that's what I was saying.
Yeah.
If you use that in kriging, and you put kriging,
yeah.
You will have.
You probably have. Probably have better results. Yeah. Yeah, that's a good point. Yeah. As I was saying, I'm not a geostatistician, but that's a really good point. So that's the type of result they got. So here they compare ordinary kriging to the regression algorithm. So what you see here are all of the elements that were predicted. In gray, this is the accuracy. No, sorry, not accuracy. The R square, which is a metric for estimating how well a regression goes, of each element, and the light. The light band is how well the ordinary kriging did. So dark gray is machine learning algorithm regression, and light gray is kriging. And as you can see here, in most but not all cases, machine learning did a little bit better, but not like a lot better. And it didn't like the elements that are not very well predicted by kriging are not very well predicted either by machine learning. But I think what's more important is when you look at the results, the the random forest, so the machine learning prediction, because it's not using spatial data, it is more it's not smoothing the results, and you get a result that's a lot more geologically plausible, or more that has more texture, I would say, and that's a lot easier to interpret. So in this case, you have to be careful because the accuracy is not a lot higher than what you would have obtained with ordinary kriging. But for interpretation in terms of textures and patterns, that's a lot better. Another example, well, I should add here, one of the best or the best parameters to estimate the soil composition was actually elevation parameter. So the above sea level high, the curvature of your slope, etc. Apparently, it's a lot better than, for example, Landsat, so satellite imagery. So sometimes the simplest data sets are the ones with the best predicting power. Another example, I think that's where there's the most buzz in the mining industry in terms of using machine learning. That's mineral prospectivity. So I'm going to give an example and show how it's done exactly. So basically, mineral prospectivity is estimating the probability of a deposit to occur on the map. Is it more here or here or here? And from there, doing interpretation and hopefully some targeting. So this example is in Spain. This is a district of epithermal gold deposits, so a lot related with alteration, specific rock types, and structures. They had for training the algorithm 46 occurrences. If you are in a pure greenfield area, you have no training data. Well, machine learning is not your solution because you can't train. And so yeah, here's an example of the input data they had. So this is a geological map, and here this is some satellite data. Apparently in this area of Spain, there's a lot of outcropping. It's very dry. So the input data, they only use public data. So geochemical survey, gravity, magnetic, of course the lithology map. This is something, sometimes it's good to use it, sometimes not, because the issue with the lithology map, it's interpreted. And you give it to the algorithm will consider that as truth. It's not going to consider maybe it's true, maybe it's not true. So you have to be careful with the lithological map. Same thing with geochemical survey. If you have a widespread and homogeneous sampling, go and use it. But if you have 10 samples here and nothing else, well, the algorithm will tell you, well, the anomaly is here, so there's a deposit here, and there's nothing else elsewhere. So you have to be very careful with cluster data because it will tend to tell you that deposits are where deposits are, and it's not going to help you discover new deposits. You want to have homogeneously distributed data. And basically, all of this data, you put it into a same grid of points. So basically, an image with pixels, and each layer of your image has values, one for lithology, one for gravity, one for satellite data. They did a lot of feature engineering to transform this raw data into meaningful data. So, for example, the hyperspectral image was pre-processed to extract alteration. The structural map, instead of just giving the place where there are faults, distance to fault was calculated, but you could have calculated density of faults, orientation of faults, many different things. And they used the 46 occurrences, but to train an algorithm, you need example of true and false. So they selected 57 barren locations to train a model, and the validation was done using cross-validation. So if you remember, that's taking part of the deposits for validation, and then others and others and others for training the algorithm. And they didn't do any final testing. That's not something you want to do because you won't get an estimation of your prediction on truly hidden data. But I happen to do that as well sometimes because you don't have enough deposits for training at all. So the idea here is don't tune too much your model. Start with 1, 2, 3 parameters that you tweak a little bit, but you know it's within an acceptable range. But don't try to overtune your algorithm, otherwise it's going to be adapted to your validation data, and it's going to be overfitted. So you have to be careful doing that. In this, well, I don't know in this case, they didn't say it in the paper, but when you want to do prospectivity mapping, machine learning algorithm, personally, I have all my algorithms ready. It's 1 hour of work, that's it. 95% of the work, that's preparing the data, cleaning, collecting, transforming the data to make it better for making a prediction. And one, I'll give that example later. And this is the kind of results you have. So you have a prediction map, which is basically 0 no deposit, 1 there is a deposit, and you see that the value is evolving depending on where you are on the map, and the black points are actual occurrences or mine deposits. And you can see it seems to fit fairly well. A good way to represent, I think, how well an algorithm is good at making a prospectivity map is this diagram. On the x-axis, you have from 0 to 100 the percentage of prospective area. So if I'm here, I'm taking the 5% most prospective area of my area of interest. Here it's 20% most prospective, etc. And the y-axis is what's the percentage of occurrences that are actual, of testing occurrences that are actually within this area. So you see that, so the algorithm I'm showing you here is random forest RF, that in 10% most prospective area you have, this one you have 90% of your deposits within it. So it's okay, it's pretty good. And some algorithms are performing better than others. And basically, at the end, you don't want it's not possible to have an algorithm that tells you this is a deposit, this is not a deposit. I wish it was possible, but it's not happening. The goal is to reduce the space in which you want to do exploration to do better targeting. It's basically, instead of looking at all the layers one by one, you take them all together using machine learning, and you produce a synthetic map that tells you, okay, in this area you have all of the parameters for a deposit to occur, so there is a high prospectivity score.
Can you talk about why the artificial neural networks would worse than the random forest?
In this particular case, I don't know why, but in general, this is the case. And I'm not using artificial neural network when I'm doing prospectivity mapping, actually. There are several reasons, but the main one is because it's hard, like it's a shallow learning problem. You look at this example, you have 36 occurrences and 57 barren locations. For the example I was showing you for training images, it was necessary for a neural network to learn rock type. I think it was roughly 1 kilometer of one rock type to learn it. And it's going to be the same thing with deposits. It's really powerful, these neural networks, but they require a lot and a lot of training data. And if you don't give enough training data, it's going to overfit your model. It's going to overfit your data. So, and yeah, that's one of the reasons artificial neural networks don't perform. But in this case, you look at the artificial neural network map, it looks a lot better. It's smooth things that looks geological, but in terms of performance, it's not as good.
So if we go back to the slide, we've grown with the areas where there's particles that are good for having normalization, right? Will this help us learn where all the new geology is different.
Yeah.
It varies from people.
It depends on two main things. One is the geologists who have provided the input data is good. I'm going to give an example. For example, you have a lithological map. And in this map, there is, for example, rhyolite A, and all of the deposits are in rhyolite, the known deposits are in rhyolite A, and rhyolite B, no known deposits. And if you gave all the rock names like that to the algorithm, it's just going to say, oh, I need rhyolite A. But maybe the geologist will think a little bit and, no, I just need a rhyolite, whatever which one, the A and the B, they're the same thing. So then you provide the name rhyolite, not rhyolite A and B, and the algorithm will be better at generalizing.
I think there's one problem where when we do our work that we normally apply as to take samples when we know that there's noise.
Yeah.
So that's one issue. And the secondary data that we want to get from remote sensing and news, they have coarse resolution.
Yes and no.
In general.
Yeah,
in
yeah.
general. Compared with small
Yeah,
samples
yeah.
that
Yeah.
compared with support.
That's where you have to be careful at the resolution of the map you're providing. If you have a geological map at 1 to 500,000, you're not going to do a 10 by 10 meters grid.
Exactly.
There's no point to that.
I looked at one of your room walls when you did the code. You had the manuscript and then the description of the density walls. Which you were trying to find what's in the
Oh, yeah, yeah, yeah.
So also there is different approach from seismic data compared to the lower data.
Yeah, I think
Did
if
you
you.
account to that?
I think I didn't. Yeah, yeah. Oh no, it was a lot more precise than that. I think it was like one data set was every 10 centimeters and the other was every 20 centimeters or something like that. So, but even though like some measurements, even if they are taken every 5 centimeters, the which one was that? Resistivity, I think. Yeah, it's measured here, but it takes into account 70 centimeters long. Yeah, that's your actual resolution, and you have to take that into account when doing prediction. That's why you have to do exploration analysis. You have to understand your data, and you have to understand the limits of your data. And sometimes the other is true. When you want to make predictions of lithologies, for example, 5 centimeters resolution is way too precise. And you want to average over 5 or 10 measurements to get a better reading, a more smooth reading. Yeah, exactly. They don't care if there is a 1 millimeter interval of shale. So again, same thing. You have to understand your data if you want to do a proper application of what you do. And that's why you don't want the machine learning application to be made only by a data scientist. You want either a domain expert, so whether a geophysicist, geologist, and a data scientist, or someone who does both. But you don't want just a data scientist because he doesn't understand. You can't know everything, so he doesn't know these little things.
Well, I believe that if the professional cannot answer the question, then the machine algorithm will never answer.
Yeah, that's a good point. Yeah, that's if a professional can't answer the question, an algorithm won't be able to answer the question. And when people ask me what's the quality of data you need for core photos to be able to make predictions, what I tend to say is, well, if by looking at the picture you can have an idea of the rock name, an algorithm will be able to do that as well. If you can't, well, the algorithm is not going to be able to do it as well. Here are the results. I just wanted to emphasize that the best, so it's possible after using a random forest algorithm, so the one they use, to extract which variable was the best predictor. And in this case, it was the first one was variable extracted from satellite data. So I guess lithological and alteration mapping using satellite data. And distance to fault are the main predictors. So you can know, okay, this data set is really good. This one is not as good. When, for example, so here PC3 is extracted from geochemistry. If you have geochemistry that's the main predictor, there's a problem here because usually it's clustered data and maybe your model is overfitted. So something I want to emphasize, what are the uses of this type of mineral prospectivity map? Because we hear a lot around. So I want to emphasize this is not generating targets. It's not because your point is red that you have to drill here. It's here to help a geologist generate targets, make informed decisions. It's not a treasure map. It's a way to integrate all of the available data to make a prospectivity a prospectivity map. It helps to reduce subjectivity. As we've seen, we know which data set is better than others, because as a structural geologist, I'll say, well, look at the faults, that's the most important, or maybe the data says otherwise. What time is it? Do we still have time for a few examples? Okay. Yeah, I'll go quickly about the last one. So this one is interpreting fractures and faults within seismic data. So if you are familiar with seismic data, it's just pixels and pixels of rock physical properties that's collected in oil and gas industry. And basically what they did, they created synthetic seismic cubes on which they train an algorithm to map the faults, because they know where are the faults in this synthetic cube because they created it. They trained the model did good on synthetic data, actually very, very well, and they tried on actual natural data to map the fractures. That's the result. So that's on the left, the raw, well, not raw, but the process seismic image, and on the right, the interpretation of the machine learning algorithm. And this one is from a few years ago, 2014, 2015, I think. Now they do things that are like, this one is already very, very good, but now it's amazing what they do. 3D prospectivity mapping. So this one is from the Integral Gold Rush Challenge. We ended up at the second place a few years ago of this challenge using machine learning. So it's basically 3D prospectivity mapping using historical data for orogenic gold. As you can see, the issue here is that the data is extremely clustered. You have a lot of data around existing deposit, a lot less around, a lot less at distance from it. So what we did is, instead of just giving the raw data to the machine learning algorithm, we interpolated and interpreted this data to create a geological model using Leapfrog, and that is what we provided to the machine learning algorithm. So from cluster data, we provided data that's everywhere on your model, even if there are still biases because of information density, and we provided that to a machine learning algorithm. Otherwise, it's the exact same process that what you've seen in 2D. So same thing, data compilation, 3D modeling. I'll put the video because it's pretty cool. So that's the actual deposit. These are the mine steps. You have underground mapping. You have boreholes with geological and assay data. It's not complex data. It's just that it's a huge amount of data. And then from that, we did a geological model. So you can see the grades, the different lithologies that were mapped, associated with gold, the structures, and all of this information, we did put it into a 3D grid of point. So exact same thing as what you would do in 2D, except it's 3D. It's just not different. And from there, we create. So yeah, we put all of this geological information in 3D, and that's the type of results we got. So just we're gonna look at this image. In purple, you see the actual stopes that have in mind, which were used as training data. And the colors from blue to red is the prospectivity score, so how likely you are to have mineralization. You can see that they stick very well to the actually mined mineralization, and we ended up with a series of targets where you don't have a mine stop, but you have high prospectivity. But that's not the end of the process. It's not just like taking these targets and saying, oh, that's all my targets. You go back, you say, oh, this is a target. Oh, yeah, there is a fault here. There's the proper lithology here. There's an intersection not too far away. Okay, this is a target. And then you rank it, and you reason, you have a rationale, and you make sure that this is a proper target. Yeah, this is something I had forgotten, but I was reminded that a few weeks ago, a few days ago, is that right before the end or right after the end of the challenge, they released new drilling, so which was not provided to us while doing the project, and with a new target, and it was in one of the targets we had proposed, so it was pretty cool. Yeah, this one I'm gonna skip it. Just using geochemical data to do a geological model, because the lithological logging from the geodesics was not precise enough in this case for what I wanted to do. So now the conclusions. As you've seen, there are many examples. Well, I tried to show you many examples showing that machine learning can be a very powerful tool. It helps making decisions. It's making a prediction. You take that prediction, you can make a decision. You can use complex data sets with a lot of different input variables. It's not a problem. They are integrated together, and you can make some sense out of it. But it requires careful training. You have to make sure you don't overfit your model. You have to make sure you have a true testing set that's hidden. You have to avoid a certain amount of pitfalls. And you need expert knowledge to provide the data in the proper format and to interpret what's coming out of it. So I think that for successful implementation, you have to implement machine learning as part of the process in exploration, in mining exploitation. It's not going to replace what's already existing. It's another tool that you can use to do things. And that's why I think machine learning is an innovation in mineral exploration. It's not a revolution. And yeah, that's it.
Are you actually able to extract their simple set, no, relatively simple set of rules that led from the input to the output, just to wait what inputs?
If you have a simple algorithm like the k-nearest neighbor we've seen at the beginning, yes. But if you have a deep neural network, it's millions of linear combinations, so you can't get much from it. Yes. There are ways to kind of having a peek at it, and it's an entire area of science. People are researching very like in different universities to actually try to get into these models, but as of today, there's nothing.
You're able to extract them, right? So the focusing
yeah, you could print it, but yeah, good luck understanding it. Yeah.
With the entire multi from you were generating like that's the underground block on the targets that you're generating. Is for actual more structure people or more development?
That was for drilling. They wanted to do targeting.
Yeah.
Yeah.
So then would eventually would this be good enough to add to resource figures? Maybe a lot that integrated to a 4311 point?
Wouldn't go there. And that comes to a particular problem when using machine learning. I have no idea what's the answer, but it's a legal issue. Is the person who is responsible for the decision at the end, the guy who trained the algorithm, or the guy who used it? I don't know, but at some point we're gonna have to solve this issue. Yeah.
Who's your qualified person?
Yeah. Well, that's exactly the point. Who's the qualified person?
I mean, I think there's has to be some validation that person really any responsible was.
Yeah.
Even mine, they are struggling now. They are still depending on treatment, and they don't really count for relations and decisions. So machine learning is
Actually,
like 100 years time. Yeah, maybe after 20, 30 years, you will find people.
Actually, there are people in Australia. I know there's an CSIRO. I've heard they are doing resource estimation, doing machine learning. I would love to audit this type of thing and understand how they do it and what they're doing exactly.
We did some research on this. It's the same idea. Like treating is like linear regression. The only treating is very tricky. You don't need to know you need only to know the distance between samples so that your variography can give you the weights.
Yeah.
The variances, right? So they, I think my friends last year when they did, they used deep intercept and as an input, they put a covariance function that comes from the variable into the estimate and put the other things together. But still, training was giving them better results.
Okay. Yeah.
They did that, but I'm not sure if like that was last year. I don't know what he's doing now. Maybe he improved his research. But still, it's a new area.
Yeah, it's research, and I don't think we will see that applied for resource estimation before. Why? Especially because this is like, or they're trying to have something standardized and a lot of quality assessment. So these new things, I'm not sure it's going to be accepted
But it will
soon.
be nice in the future that machine learning algorithms actually also answer things. I know that there's some things that you
Oh yeah.
you know, like different scenarios, and then you make
Yeah.
decision on how to answer things. Because one answer, I don't quite know myself. You know, like someone gives one answer, I don't.
But because you're a geostatistician,
Yeah.
the engineer wants
Like, yeah,
one answer.
I know, but like, yeah, it's like always you make decision under a certain and you have to take some risk.
So yeah. So in this case, this is using a random forest. So it's an algorithm that's based on trees. So to make it simple, this is classification tree. So basically, you take all of the data and you try to divide using one variable at a time your data set. So for example, gold, not gold. Let's say there is sulfide, or there's more gold if there is sulfide. There is less gold if there is less sulfide. That's one split. Then in the one with sulfide, if this is chalcopyrite, if there is more chalcopyrite than pyrite, more gold, and less gold if there is less chalcopyrite. You divide little by little to make it simple. So what it's doing, it's looking at all of these splits and which variable has been able to contribute more to these splits, give more purity to each split. So if it's a bad split, it's going to give, it's going to split, but it's not such a good score. But if it's splitting perfectly gold and not gold, well, that's a high score, that's a very good variable. So very simplified, that's how it works in this particular case. But yeah, there are other algorithms with other ways to do it. Yeah, because in this case, so this random forest, it's not one tree, it's 100, 300 trees, and they are in part random, that's the name. They randomly select some variables are not used. So it's really testing all of the different variables. That's why it's more powerful, and that's why you can rely.
Every tree is wrong, but then you know,
Yeah, exactly. No, that's exactly.
Each tree is wrong, right? So you cannot make a decision on it, but you decide everything.
Yeah, that's very similar, and you can actually estimate uncertainty related to these trees actually using the difference between all of the trees. Sorry? Yeah.
Because random forest in a lot of these methods, one of the biggest problems is you have something linear unknowns that aren't part of the ranges.
Yeah.
Interrogating the percentages.
Yeah.
Within the random forest.
Yeah. And every time I do prospectivity map, I also provide the uncertainty map for the client to see, that's what the uncertainty is, and maybe I have to collect more data of this type or this type, because in this area there's a lot of uncertainty, in this area less. Yeah.
Normally you optimize your decision based on uncertainty. So you have uncertainty and this is the profit. Normally you have right profit until it's high uncertainty. So now you do like efficient frontiers in business and try to find which location you like to create.
In theory, that's what we're supposed to do in theory. In reality, we tend to look, there's a nice red point here.
Yeah, let's go here. The manager said here.
Yes. For what? I use an algorithm that's been done by people who are way more clever than me. That's used, are you familiar with random forest? With outer flag estimate. I don't remember the name of the name. That's the one.